This is a video lecture for Math 283, and the topic today is lines in space. This is found in section 12.5 of the textbook. Now I want to mention to you that I'm splitting section 12.5 into two, and today we'll be talking about lines in space, and the next class we'll talk about planes. Okay. If we have a line in 2D, there's a simple way to define a line or create a line in two dimensions, and that's to have 2 points will define a line. Another way we can define a line in 2D is we can have a single point and a slope. In 3 dimensions, the situation is fairly similar to that. We can either define a line in 3D by having 2 points along that line, or we could define it by having a single point along a line and having a direction. Okay. So let's consider this scenario. We have a line that passes through the point P1, x1, y1, z1, and this line is parallel to the position vector A that goes from the origin to the point A1, A2, A3. Okay. These, by the way, you could write vector A. If you write vector A in components, that means vector A is A1, A2, A3. These numbers here, these components, are referred to as direction numbers. As direction numbers of this line, keeping in mind that vector A is parallel to this line. So these direction numbers define a certain line. I should mention, though, that they're not unique. Basically, any scalar multiple of these direction numbers will still apply to this line. Okay, so that's an important point. Okay, so imagine we have another point, Pxy, and we look at the vector P1, P. Okay, this vector is parallel to the vector A. Okay. Now, another thing to keep in mind is if I take any vector A and I multiply by a scalar, so if I take t, some scalar number t, and multiply by A, this vector is parallel to the original vector A. Okay. So imagining that P1P is equal to TA, let's imagine that P1P is equal to TA. Okay. And this has to be true. It has to be true that P1P is some scalar multiple. This vector is some scalar multiple of the position vector A. So we know this is true. P1P is equal to some scalar times the vector A. But we can, in terms of these points, we can actually write out what these vectors are. So vector P1P is equal to, and the way we find a vector between 2 points is we subtract this final point. We take the final point, subtract off the initial point. So this vector is x1 has components x1 minus, or x minus x1, y minus y1, and z minus z1. Okay. But we know this is equal to a scalar multiple times A, so this equals t times the vector a1, a2, a3. Okay. In other words, this is equal to, if we multiply through by t, we get ta1, ta2, and ta3. Okay. So these two vectors, p1p and ta, are equal. Okay. Now, if two vectors are equal, that means their components are equal. And so I can equate these components, and I get these equations x minus x1 equals equals ta1. Y minus y1 equals ta2, and z minus z1 equals ta3. I'm going to box these equations. These equations are known as the parametric equations of a line. So these equations specify each point x along a line, but they specify them in terms of a parameter t. So it's not like we're relating x to y. We're relating x to a parameter t, but each coordinate x, each point x, y, z is related to this parameter t. So these are parametric equations in terms of t. We'll talk more about parametric equations later in this course. Let's see, what else did I want to say about this? One thing to note here is I mentioned to you guys the direction numbers are not unique to a line. The other thing that's not unique is the point x1, y1, z1. Okay, this is some particular point along the line. We could change our point, our p1 here, to some other point and have a different point, and we could have different direction numbers. The direction numbers will have to always be a scalar multiple of each other. But that's an important point, that these are not unique equations of a line, but they do define a unique line, if that makes sense. Okay, so I'm going to keep this, I'm going to erase what's up here. I'm going to keep what's downstairs here. There's another way we can write the equations of a line. And what that has to do with is if we solve for t in each one of these equations, let's say we solve for t, okay? So in the first equation, t equals x minus x1 over a1. In the second equation, t equals y minus y1 over a2. And in the third equation, t equals z minus z1 over a3. Now I'm going to box this equation, and these are known as the symmetric equations of a line. So this is another alternative to expressing the equations that describe some line in 3 space. Now these equations don't involve a parameter, so these equations directly relate x, y, and z to each other. And by the way, I should mention that we can't have a1, a2, and a3 cannot equal 0 in these equations. For obvious reasons, we don't want a 0 in the denominator. Although, if it happens that one of our direction numbers is 0, there's still a way to deal with that. We just exclude that particular equation and we look at the other 2. Okay, let's do some example problems involving finding some equations, both forms of equations of various lines. So I want to do 2 example problems. The first one has to do with, we want to find the equation of a line that passes through the point 1, 5, and 2, and is parallel to the vector 4, 3, and 7. Okay, so we want to find the equation. And by the way, let me, just for reference, let me write down, I have my symmetric equations. Let me write down the parametric equations. X minus x1 equals a1t. Y minus y1 equals a2t. Z minus z1 equals a3t. So I want to find both the parametric equations and the symmetric equations of this line. It's defined by this point and this direction. So these are the direction numbers of this line, or one example of the direction numbers of this line. So if we want to write down the parametric equations, that's pretty easy. We're going to write down x minus x1. x1 is 1. So x minus 1 equals a1, which is 4 times t. Y minus 5 equals a2, which is 3 times t. And z minus 2 equals a3, which is 7 times t. These are the parametric equations of this line. Again, these are not unique. We could have chosen another point. We could have chosen another scalar multiple of our direction numbers. And let's see if we can write down the symmetric equations of the line. That's also pretty easy. So here we have x minus 1 divided by 4 equals y minus 5 divided by 3 equals z minus 2 divided by 7. These are the symmetric equations of this line. Now another more interesting question is, where does this line intersect the YZ plane? Where does this line intersect the YZ plane? How do we answer this question? Well, for the YZ plane, we know that x has to equal 0 throughout the YZ plane. And so what we can do is set x equal to 0 in either one of these equations, but it'd be easier to do the symmetric equations. Set x equal to 0 as a first step. And so if we do that, we get 0 minus 1 over 4 equals minus 1/4. But by the symmetric equations of a line, we know this is also equal to y minus 5 over 3, which is also equal to z minus 7. Did I put 2? Oh, sorry, z minus 2. I'm getting confused there. Z minus 2 over 7. And now what we can do is solve for y and z to find the point at which this line intersects the yz plane. So there's two different equations here. If I solve the y one, I get, let's single them out. Y minus 5 over 3 equals minus 1/4. I can multiply by 3, and I get y minus 5 equals 3/4. And now y will equal 5 minus 3/4, which is 20/4 minus 3/4 is 17/4. Okay. And I can also solve for z. Z minus 2 over 7 equals minus 1/4. So z minus 2 equals minus 7/4. And z then equals 2 minus 7/4. 2 is 8/4. This equals 1/4. So this is cool. I found the point at which this line intersects the yz plane, and that point is x equals 0, y equals 17/4, and z equals 1/4. So that's where that line will hit the yz plane. That's a good, straightforward example problem involving using these equations. Let me do one more example problem. In this problem, we're given 2 points that lie along a line instead of a point and a direction. So imagine we have one point, P is 1, 2, minus 1, and another point Q, which is 5, minus 3, and 4. We have these 2 points along the line. We'd like to find both the parametric and symmetric equations of this line. Okay, how do we do that? Well, what we can do is construct a vector PQ, okay? And this vector PQ will be parallel to the line that passes through PQ, okay, by definition. And so let's construct this vector, and we do that by subtracting. Actually, do I want to do QP or PQ? Going from P to Q, so I'll take the point Q and subtract off P. So to find my components, I get 5 minus 1 is the first component. The second component is minus 3 minus 2. And the third component is 4 minus a negative 1. And if we simplify this, we get 4, we get minus 5, and we get 5, it looks like. Let me just double check my notes. That's right. So now, these are now the direction numbers of this line. Again, these are not unique, but these define a vector that's parallel to this line. And now to get my equations, I can just choose any point I feel like along the line. So it doesn't matter, I could choose P or Q. Why don't we choose P? So to get the parametric equations of the line, that means S minus 1 is equal to 4t. Y minus 2 is equal to minus 5t. And z minus a negative 1, which is z plus 1, is equal to 5t. So these are now the parametric equations of this line. Let's also write the symmetric equations. So we get x minus 1 over 4 is equal to y minus 2 over minus 5, which is equal to z plus 1 over 5. These are the symmetric equations of the line. And so we solve for the equations of this line. That's another good example problem. There's one more topic I want to cover, but I'm going to wait to talk about it in class with you guys. And it's basically an example problem where we show that if in 2D, if you have two lines in 2D, if those two lines are not parallel, they have to intersect somewhere. That's not true in 3D. Okay, so you can have two 3D lines that are not parallel, that do not intersect, and those are called skew lines. And on our next class, I will do an example problem involving showing that two lines are skew lines. So I'll see you guys next class.